Welcome back, kids, to the last summer packet video. Again, if this is, these last 2 pages are only required if you are going to BC Calculus, but even if you are not going to BC Calculus, you are absolutely welcome to try these problems as well. So, page 8, vectors. Woohoo! Remember those? All right, vectors. So, given 2 vectors v and w. So let's do a little bit of a drawing here before we just jump into answering. Remember, the power of vectors is that while I conveniently talk about them as being going from the, from the origin, vectors really can be picked up and placed anywhere, which is a lot of their power. So remember, vectors can be in a number of different forms as well. This is in what we call the ij, and since it is just I and j, I'm in 2 dimensions, not 3. I, j, and k would be 3 dimensions. And the I is the horizontal component, and the j is the vertical component. And remember, I is a unit vector, and the unit vector is 1 unit only in the horizontal and none in the vertical, and the unit vertical is 0 horizontal and 1 vertical. So this is -2 times the unit vector. And remember, I can write things in vector notation, like -2, 5. I could also write that as vector v. IB likes to write vectors in this vertical format. Neither AP nor IB care how you write your vectors, but you have to recognize all of the notation. Okay, the IJ notation, the component notation, or the IB notation, vertical component, horizontal component, vertical component. AP tends to use either IJ or component. Horizontal component, they don't tend to use the vertical alignment. Nevertheless, this is actually V is -2 times the unit horizontal vector 1, 0 plus 5 times, and what that means is basically plot the point -2, 5. So -2, 5. And from the origin, go out there. So that is V. W is 3, 4. Okay, so this is vector V, and this is vector W. So if they want to know what half of V is, well, half of V would look like this. Right? About half of it. And how you take half of it is take half of the vertical and half of the horizontal. So that is just, half of -2 and half of 5. Okay? Or again, I could write it as -1 I and 5 halves j, or just -I and 2.5 j. But again, we tend to stay away from decimals. Okay? So that's pretty simple. That's a scalar multiplication, right? A scalar multiplication of the vectors. Now, this one So I could double it, I could negate it, I could, um, right? It's a dilation factor, really. Now, when you want to subtract two vectors, I want you to think of taking W, which is here, and I'm subtracting V. That means when you think about this graphically, you're taking the vector V here, tip to tail, and you are adding the opposite of vector V. So you're taking vector V, which tip to tail, and you are adding its opposite to the tail, right? So I'm going to start here at the tail of W and make a parallel, taking this vector like I'm copying and pasting it, right? Copying and pasting this one here, but in the opposite direction. Or you could think of doing, right? Taking the opposite of V and putting it at the end of V, putting it at the end of W. That's what subtraction of vectors means to do. So now the question is, where did I land? And I want to represent that with the vector from the origin. And how I figure out what that is just do the subtraction with 3 minus negative 2, right? 3 minus negative 2. And 4 minus 5. Or again in IJ format. And if you think about that, even with my pathetic drawing, 1, 2, 3, 4, 5, and down negative 1 is the vector W minus V. Now, dilating a vector gives you a vector. Subtracting two vectors gives you a vector. The magnitude, yes, though I know those are absolute value bars, but we think magnitude in vector land, but it is kind of, it's a distance, which absolute value is a distance, right? And this is not a vector. The magnitude of a vector is a distance. It is a distance, therefore it is positive. And it's not a vector, it is a value or a number. Okay. So I'm going to erase some of the things on my drawing. So I just want to know the length of vector V. So the length of vector V this entire length, how long is that? Knock, 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 knock. Do you hear that? Who's coming in? It's Pythagoras! Pythagoras helps me get the magnitude, right? Right? If I want the length, look at that. It's a hypotenuse. How do I get the length of a hypotenuse? Pythagoras comes to my rescue again. Oh, that Pythagoras, I do appreciate him so. Right? So how far did you go in the horizontal? Square it. How far did you go in the vertical? Square it. Add them together, get the square root, and you get the magnitude of W. Right? So how far did I go in the horizontal? 3. How far did I go in the vertical? 4. 3 squared is 9. 4 squared is 16. Add them together and I get 25. The square root of 25 is not plus or minus 5. It is 5. I didn't ask for it, but could you find the magnitude of vector V? Even though vector V is going right up into quadrant 2, the magnitude of vector V would be the square root of negative 2 squared plus 25, positive distance. positive, right? This is approximately 5 something, right? 5 point blah, 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 blah. It is longer than vector W. Vector W is shorter, right? Vector W is 5, vector V is length square root of 29, which is bigger than 5. Okay, let's do a little bit more. Oh snap, they just asked me about the magnitude of V. We just did that, right? So I wanted to be clear that I could ask you in notation, or I could ask you like this. Since we already figured that out, let's find the magnitude of that vector I erased, right? I erased the picture of, but I didn't erase the value of it. Right? W minus V is 5A minus J, so what is the magnitude of that vector? Five squared, which is 25, plus, excuse me, 1 squared, which is 1, square root of 26. Also bigger than 5, but in between, right, vector, this vector is smaller than vector V, but bigger than vector W. Yes? All right, so those are a brief review of the operations, regular operations with vectors. But how about this, the dot product? That looks like a multiplication sign, but in vector land, that is called a dot product. There is a formula that you can just straight up memorize for the dot product, but it is not regular multiplication like it is with numbers, right? It's a formula, but what the dot product is, the dot product is not a vector. The dot product is a number, and that number describes how parallel these two vectors are. So that means that if you aren't parallel at all, you must be perpendicular, right? So if the dot product is 0, the two vectors are not at all parallel, which means they're perpendicular. Now, the actual value besides 0 of the dot product is not, you don't have to worry about the magnitude of the dot product. You just have to worry about whether it is 0 or not, or kind of big or small relatively. And here's what I mean by that. So again, I'm going to do a little bit of erasing on this diagram. Oh, rats, I didn't mean to erase that. So, with this, and I haven't even really drawn it this to scale at all, but look at the angle between these two. That angle, I'm not asking what that angle is, except, is it 90 degrees, right? Those two vectors are not perpendicular, so the dot product should not be 0. It should be a number, right? So let's compute it. Now they look not that close to being parallel, right? So the larger number out of the dot product is the more parallel. The smaller the number is, the closer you are to 0, the more perpendicular you are. So let's compute our dot product. So here's the formula for the dot product. Oh, I've got to write down, I forgot what W and V are. Whatever. I'm going to do the dot product on this page so that I can see what V and W are. So it's take the dot product is the product, the dot product is a sum of two products. And it is the product of the horizontals plus the product of the verticals. So that's -6 and 20, which is 14. Okay. So 14 is a value I don't have to worry about. It's not 0, so my vectors are not perpendicular. It's relatively, it's not like 99, right? So these vectors aren't that close to being parallel. All right, so that's all the dot product is. The dot product is the product of horizontal added to the product of the verticals. You'll use dot product in physics also, and they'll give you an alternate formula for the dot product that involves the actual angle, because in physics you get a lot more information about angles. In math we get a lot more information about the actual vectors themselves. So that's why our dot product, we more often use the formula that involves the information from each of the vectors, whereas in physics you'll get a formula that involves the angle, because you're able to, like I said, know the angle in between the vectors more often in physics applications. Okay, so remember so the dot product, we got 14. Now, how about this? Since addition and multiplication is commutative, what do you think the dot product of V dot W would be? Yes, the same, right? Because both multiplication and addition are commutative. All right, changing topic a bit. Now we're going from, so we did some parametric stuff in the previous video. We did some serious stuff in the previous video. Now we're doing we did some vector stuff in this video, and we're doing polars. Those are the 4 main topics that are BC specific, that are not tested on the AB calculus exam. So this is just, again, background knowledge. Can you do the conversions between a rectangular and polar system? So I'm going to draw a graph here. And I'm going to graph both polar and rectangular on this same system. So this is in rectangular form, which means it's x, y. So I'm going to plot that point. 1, 2, 3, 4. There's 4, right? To do anything in polars, especially any conversions, you do need some formulas. So here are the formulas that you need. And AP does not give you formulas. You need to know that x is equal to the radius times the cosine of the angle. Y is equal to the radius times the sine of the angle. The radius, shocker, hello, Pythagoras, you're back. Oops, sorry. The radius squared is equal to x squared plus y squared. Theta is equal to the inverse tangent, which you studied in Algebra 2 and pre-cal, of y over x, with the fine print that you have to think about the quadrant that you are in. So you make sure you have the right sign, S-I-G-N. So this is an x and this is a y, right? They gave me an x and a y. So how do I convert that to polars? And polars, if you remember, polar coordinates are the radius. How far do you radiate from, instead of the origin, we call it the pole. And what theta do you rotate to get to your position? And when you're rotating theta, you're rotating from standard position, right? Standard position is the positive x-axis. So how did you rotate from the positive x-axis to get there? So I started with this problem because 4, 4 is a really nice, hopefully you can picture that that is, right, 4, 4, if I were to draw the shortest distance out there, right, that cuts the quadrant in half without any, right, without any conversion or any formulas. I hope you understand that that's pi, that theta is pi over 4, right? Remember, we don't talk in degrees, right? Pi over 4. So let's verify that. So they gave me x and y and I want r. So I don't need to find x, I don't need to find, oh, here it is. I need to find r. So r squared is equal to 4 squared plus 4 squared. R squared is equal to 16 plus 16. R squared is equal to 2 times 16. R squared is equal to 2 times 4 squared. R is equal to the square root of 2 times 4 squared. But then therefore r is equal to, since 4 is squared and you're taking the square root, the 4 comes out and it's 4 radical 2. So r is 4 radical 2. Now I went through all that. I don't actually write all that stuff out, and if you had written r, this is equal to 32, and if you had just said r is equal to the square root of 32, that's absolutely fine. It's just that this is multiple choice. 4 root 2 is going to be there, not the square root of 32. So I needed to find r. I used the formula to find r squared, and then just the square root of it. To find theta, I say to myself, I'm in quadrant 1, and if I'm in quadrant 1, tangent is positive. So I take who has a tangent of 4 divided by 4, which is who has a tangent of 1 in quadrant 1. That's pi over 4. Oh, I already knew that. Right? So what does that mean? In polars, to graph this in polars, you would go out from the pole a distance of 4 root 2, which is a little bit more than 4, and then you would rotate pi over 4 degrees. I'm sorry, pi over 4 radians, right? And you would land at the same position as 4, 4 in rectangular land. Right? So in rectangular land, from the origin, the shortest distance, right, linearly, is this way, right, is diagonally out this way. That was a length of 4 root 2. To graph that in polars, I radiate out a distance of 4 root 2, that radius, and then I rotate pi over 4 degrees. I keep saying degrees. Pi over 4 radians. But nevertheless, whichever way I do it, I land here. Again, the purpose of polars, there's a lot of non-function graphs in polars that I can represent in polar form as a function. And then I can do a bunch of calculus on that. So let's go backwards. we're going to convert 2 pi over 6 to rectangular coordinates. So remember, this is r and this is theta. So to graph this, in polars, I radiate out a distance of 2. My radius is 2. And then I rotate pi over 6 radians, which is 30 degrees. Right? How do I get those rectangular coordinates? Right, it's 2 pi over 6 in polar. How do I get that in rectangular? So they've given me r and I need an x. There's a formula for x. So x is equal to the radius times the cosine of pi over 6. And y is equal to the radius times sine of pi over 6. This is why you thank your pre-cal teacher for all those speed trigs. You cannot spend a bunch of time thinking about pi over 6. I got to convert that to degrees, and then I have to think about my unit circle or triangle. No, you just have to know that the cosine of pi over 6 is root 3 over 2. And the sine of pi over 6 is a half. So the rectangular coordinates root 3 is like 1.7-ish. So it's like 1.7-ish and up 1 lands me at the same place. Cool, huh? All right, let's do some graphs. Now, when you were in pre-cal, you should have done tons and tons of polar graphs, all kinds of different kinds, all, explored them, graphed them, used your calculator, didn't use your calculator. AP doesn't need you to know all of those. So we've given you a couple of the favorites, the basics. If it's a hard polar, they will either give you the graph, a hard polar, a difficult polar equation or a more complicated one. They will either give you the graph if you don't have a calculator, or they'll put it on a calculator portion. But these are basic polar functions. You do need to know that this form, when you've got a subtraction or an addition, this is some kind of, right, it's either a Limousin cardioid situation. Now, here's how I know without my calculator. I think about this in rectangular form, and I know trig so well, I know what that looks like. It's cosine, negative, starts at a min, its amplitude is 3, from a sinusoidal axis of 1. So it's going to start at a minimum. If I have to go a distance of 3, that's at -2. So it's going to go like something like that. The only thing I care about this is that there is a portion below the x-axis. That means I'm going to have a loop, a limousin with a loop. If you don't remember this, that's okay. You've got a lot of time to review it. That's one of the things we're doing. Also, cosine goes with x, which means it's a right or left issue. With the negative means left. So I don't have to do a super great picture of this, but it's going to look something like a small loop with a big loop oriented to the left, right? That's really all you need to, that's as much as you need to do in calculus, right? I don't really, because what we're going to do in calculus is actually find like the area of the big or the small, or just the big minus the small, or all that kind of stuff, right? So we don't actually need, I don't need to be any more fancy than that. With no plus or minus, I do need to recognize that this is going to be a rows situation. And a rows situation that is a sine rows means that there are actually n petals. This is my n, and this is the length of the petals. Sine is a y issue. Kind of, sort of looks, oh, that's terrible. Terrible. So that's as much as you need to know without a calculator. But often you are given a calculator with polars. So let's get our calculator out and put it in polar mode. So go to mode, over to polars, and let's graph 1 minus 3 cosine theta. Go ahead and hit mode again just to verify that you are in radians. Hit window, and I do want to go all the way around 0 to 2 pi. T-sep is small. Now think about your x and y min, right? We said this was length 3, and it goes out to the left. So this is why I'm telling you that sometimes if you have your calculator, in order to set your window well, you need to know that you do need to know that IB need to be a little bit further, right? To the left. I don't need to go all the way out to -10, and I don't need to go down to -10 either. Ah. And let's graph this thing. There you go. Hit trace. And notice that there's my graph, 1 minus 3 cosine theta. When theta is 0, I'm out at -2. The rectangular coordinates are -2, 0. If you want to see the polar coordinates, go to second format and turn on polar coordinates. And now notice when I hit trace, I get polar coordinates down here. R is -2, theta is 0. So that's in rectangular, that's under the x-axis, above the x-axis, above the x-axis, and below the x-axis. And then it will stop. So again, look here, look at my, right? Did you see how the cosine graph, 1 minus 3, is under the x-axis, above the x-axis? That's the large part of this Lima saw. And then again, back under the x-axis. So these two under the x-axis pieces make the little loopy thing. Let's change this to 4 sine. Oh, that's not what I wanted to do. 3 theta, right? So we said since it's sine, the petals are going to be length 4, so my window should still be okay, right? And I'm going to have 3 petals. There you go. And if I hit trace, There's my rows. Okay. So for the important components to your polar graphs is that you have a basic snapshot, that you can have some basic information about some of your basic limacon cardioids, right? A limacon cardioid some number plus or minus b sine theta is going to either look like it's either going to look like that, where it kind of looks like a heart, and either that heart comes down and touches the pole or it doesn't, or it's going to kind of look like the loopy. Terrible, right? Some cardioids come down and touch the pole, some of them are above it. R equals A plus or minus B cosine theta are cardioids that look like that, or it's a limacon if it touches the pole, or a loopy limacon. That's terrible. That's not too bad, I guess. Right? This is positive sine. Negative sine would be upside down to that. This is positive, or negative cosine. I should have done it the other way. Right, for positive. Positive cosines would be over here in the right. Okay, and your roses have n petals, but for cosine it's 2n. Right. Cosine is even. Remember it that way. Sine is an odd function, so it's 1, which is odd number, n petals. Sine is even, so it's 2 n petals. All right, that's it. You are done with your summer packet, and I hope you found a lot of extra nuggets in here that through these videos of tips and hints and places where we're going to use this in calculus. But congratulations, you are done.